Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest, make K-Subarray sums equal. The problem states that you are given a integer array and another integer k. The given array is circular. It means that let's say the array is 1413. So the next element of 3 would be the first element, which is 1. And similarly, you can say the previous element of 1 is 3, right? So the array is circular. Now you can perform the following operation any number of time. What is the operation? Operation is you will pick any element from the array and increase or decrease it by 1. You need to return the minimum number of operations such that the sum of each subarray of length k would be equal. So for example, let's say the subarray, the array is 1413 and k is 2. So what does it mean? It means that we need to return the minimum operation in which we will be able to make the sum of each subarray of length 2 equal. So how many subarrays of length 2 are there? So you can see this is the first subarray 1 and 4. This is another subarray of length 2, 4 and 1. This is another one, and there's one more, 3 and 1, because the array is circular. So this is also another subarray of length 2. Now we have to make everything here, the sum of every of this subarray equal. Currently they are not. You can see this subarray has sum of 5 and this subarray has sum of 4. So currently they are not. So one way to make them equal is we just perform one operation on index 2 and reduce 4 to 3. So the new array is 1313. Now you can check every subarray of length 2 have equal sum. So you can see this subarray has sum of 4, this subarray has sum of 4, this subarray also has sum of 4, and finally this subarray, the which includes the last and the first element, also has sum of 4. So with just one operation we are able to make the sum of every subarray equals, and hence the answer here is 1, right? So hope the problem statement is clear. Now uh, before jumping ahead, I would like to tell you that this is a bit tricky problem. So stay till the very end, and I'm very sure you will be able to understand each and every aspect of this problem by the end of the video. So stay tuned. Now, as always, before solving this exact problem, let's try to tackle uh, the reduced version of this problem first. So the current problem states that you have to make the sum of each subarray of length k equal. So instead of dealing with subarrays directly, let's try to make each element of the array equal. So the reduced problem is, given an array, return the minimum number of operations in which every element here would be equal, right? So if you haven't thought about this reduced version of the problem yet, I would encourage you to pause the video and try to solve it yourself first, right? Now we need to make every number here equal. So you can see the order of element doesn't matter, right? We just need to make everything equal. So as always, if order of element doesn't matter, the first thing that you should do is just sort the array, because sorting gives you, like, sorting open up lot many different possibilities to solve the problem, right? So we just sorted the array. Now we need to make everything equal. So after performing the operations, everything here would be equals to x, right? Now what are the different value of x? I would say that the different, firstly, like, x will never be less than the smallest value here. So x will never be less than 1. Why? Because if x is less than 1, it means, let's say, we need to make everything here as 0. Like, what we are saying is we are making everything here as 0. So instead of making everything as 0, we can make everything as 1 first, right? And then from this only we will be able to going to 0, right? Because 0 is less than 1. So after coming to 1 only we will go to 0. So now we will apply one operation on each element to go to 0. So we'll apply 6 more operations to go to 0. But we need to find the minimum operations, right? So why are we wasting 6 operations here? We can just stop here, right? We can just make everything equals to 1 and stop here. So that's where what we are saying is it doesn't make sense to convert everything to to a number which is lower than the smallest element, right? You can always stop at the smallest element, and that will give you more optimal answer than anything less than that. The same argument is applied for anything which is greater than the largest element. in this case 6, right? Now there are still many elements in this range. So currently there are only 6, but in original problem the range is up to 10 to the power 9, right? So the element here can be, let's say the first element was 0 and last element was 10 to the power 9. So this range is still used. We can't iterate over this range, right? So that's where the next observation is, we will only keep the value of x which exists in the array. For example, the value of x will never be equals to 4 or 5, because 4 and 5, like there is no element which is equals to 4 and 5. Now why this is the case, I am not showing you complete proof, otherwise this video would be very very huge. I can post that in the comment section below if you are interested, but just to give you intuition, let's say we are making everything equals to 4, right? So if we want to make everything equals to 4, what will we go through? So basically this 3 would become 4, right? This 3 will also become 4, this 6 will become 4, and these two 2's will also become 4. So notice that what we are doing is, we are going through one of the element which is just smaller than 4, and also incrementing the elements which were equal. So we are wasting two operations here first of all, and then we are also wasting three operations for all the elements which are less than 4, right? So basically, to go from 1 to 4 you have to go via 3, right? So you can simply stop at 3 and save some operations here. So that's the basic intuition why anything which is not present in the array would not be an optimal choice. So again, for complete proof, I can link that in the comment section below. Now, what we know is the possible value of x. So in this case, the possible values of x are 1, 2, 3, and 6, right? So these are the four possible value of x in this particular case. Now, what you need to do for each of these value of x, you need to find out the number of operations that you need to make them equals to x. So for example, let's say x is 2, right? So we need to figure out how many operations are required to make everything equals to 2. So in this particular example, to make 1 to 2, you require one operation. Basically, you have to increase 1 to 2. To make 2 is already 2, so you don't require anything here. Similarly, you don't require anything here. To convert 3 to 2, you again require one operation. Again, to convert 3 to 2, you require one operation. To convert 6 to 2, you require four operations. Basically, you will be decrementing 6 four times, right? So you require four operations. So in total, we require 7 operations to convert everything to equals to 2. So we'll perform this exact same calculation for each of the possible value of x, and whichever gives us the minimum will be our answer, right? Now, what is the time complexity of this entire algorithm? The time complexity would be the number of distinct value of x multiplied by, for each value we are iterating over the entire array to get to calculate the minimum operations that we need, right? So basically n, right? Now how many different values of x are there? We just see that only we will only consider the values which are present in the array. So in worst case, all the elements of the array are distinct. So the value of x would be n. So there are n distinct value of x. And for each of these distinct value of x, we will be iterating over the array again to find out the score. So the complexity would be order n square, right? Now, the given problem was harder than this. So, and that also doesn't allow n square. So basically, we should not, or we can't afford n square complexity for this reduced version of the problem, right? So we have to optimize it. Now, which of these two factors you can remove? We can't remove x because we have to iterate over everything to get the minimum, to get the optimal answer, right? So we have to try to remove n. Now, what does it mean? It means that we want to calculate the number of operations required to make everything equals to a particular x without iterating over the entire array. in just order one time, or order login time, right? Something of that sort. So how would we do that? Again, encourage you to pause the video and try to think once by yourself. So let's see. Let's say we need to make everything equals to 2, right? So what exactly are we doing? We are converting everything greater than 2 to 2. So we are subtracting, or we are applying decrease operations on all these elements, right? And similarly, we are applying increase operation on all these elements, right? Now, how many increase or decrease operations you need? So everything here at the end will be 2, right? So in total, the sum, so 3 would be 2, 3 would be 2, and 6 would be 2, right? So in total, the sum here would be 6 at the end, right? And currently the sum is 9 plus 6, 15. So, sorry, 6 plus 6, 12, right? So currently sum is 12, and after the fact it would be 6. So we can simply subtract this 2 to get the number of operations required to make everything equals to 2. Notice that we are able to do this like sum minus uh, the resultant value, because we know that we are subtracting from everything, right? We can't do this exact same thing if we are adding to something and subtracting to something, right? We can't do this because that would that would contribute more to our answer, right? So for example, let's say we can't say that, okay, just take this one as well. So we can't say, okay, we have 5 element, we need to make all these 5 elements equals to 2. So let's just sum everything. So sum would be 6 plus 3 is 12, plus 2 14, plus 1 15. Total sum is 15, and after everything is done, the sum would be 10. So we can't say that 5 operations is enough, because we just saw that we require 7 operations, right? So 5 operations is surely not enough. So this will not give you correct output. And the reason why it doesn't give you correct output is because you are adding to something which will be like basically you can see 1 will be converted to 2, and 6 has something extra, and that would be converted to 2. Now if you add 6 and 1, you will lost the factor that you are decreasing 6 and increasing 1. So it will become that, okay, sum is 7 and we want sum to 4, so just decrease 3 times. But that's not the case. We have to decrease exactly 4 times, and you have to increase 1 time, because these two are different elements. But if we combine them, then they will become same element, and we'll lost this extra one operation from here and extra one operation from here, right? So that's why it is very important to segregate the positives from the negative ones. Basically, we need to understand which all elements will be subtracted from and which all elements will be added to, right? So we need to keep these two things separate. So in this case, we know these three elements will be subtracted. We'll be subtracting numbers from these three elements. So the sum of these three elements currently is 12, and we want sum to be 6. So in total, we require 6 operations to convert everything equals to 2. Now for the left part, we know the sum is 3 and we require sum to be 4. So we require exactly one operation to convert everything to equals to 2, right? Now this, what is variable in these two case? The variable is, we need to understand what is the current sum, right? And second thing we need to understand is how many elements are there to the right and how many elements are there to the left. So currently in this case, there were 3 elements in the right. So that's where the total expected sum was 6. And similarly, there were 2 elements in the left. So the total expected sum was 4. So we need 4 things: number of elements in the left, number of elements in the right, sum of all the elements in the left, and sum of all the elements in the right. Now all these 4 things is something we can get in order one time. So number of elements in the left and right is, you can just simply do n minus I to get the elements in the right, in the left, and I minus 1 to get the elements in the left, right? For getting the sum, you can simply use prefix sum. So you can use prefix sum to get this particular sum. You can use prefix sum to get this particular sum, right? So all these four things which we need to calculate the number of operations are can actually be computed in order one time, and hence we can simply get rid of this n completely. So what we will do, we will simply iterate over each of this number. For this number, let's say we want to make everything equals to 1, we will say how many elements are there which are less than 1, what are their sum, how many elements are there which are greater than 1, and what is their sum. Just apply this formula and get the number of operations that will be required to make everything equals to 1, right? So if this part is not clear, I would encourage you to watch this part again, just to make your understanding clear on this part, because this is the base of the problem, right? So the pseudocode for this would look something like this. So it we will be doing exactly similar to we will be doing exactly the same thing that we have discussed just now. We will initialize our answer with something which is very huge, right? Because we want the minimum number of operations, right? Now for each I, we are trying to make every element equals to the current element I, right? So for that, we are finding out the number of elements which are smaller than array I, which is I minus 1, number of elements which are larger than array I, and number of elements which are smaller, like which number of or sum of all the elements which are smaller than array I. Similarly, sum of all the elements which are larger than array I, right? So now notice that we are able to do this only because we have sorted the array. If we wouldn't have sorted the array, this prefix logic would not have been applied, right? So because we have sorted the array, we can simply say that all the elements in the left are smaller and all the elements in the right are greater, right? Now, once we got these three, we can simply calculate number of operations required in the left part, right? And number of operations required in the right part. And just sum both of them to get the total number of operations to make the entire array equals to array of I, right? So again, if you have any doubts in this particular part, just rewind this particular section and try to understand this part first, right? So till now we have solved very smaller version of the original problem. The original problem states that we need to return the minimum number of operations such that the sum of each subarray of length k is equal, right? So let's now try to tackle that. So firstly, the problem states that the given array is circular. So if let's say the starting index is 2 and we are going we are going, let's say, in this direction, right? So the array was 2 3 4 1 3, let's say, right? And what the problem states that we the next element of 3 is equals to 2, right? And similarly, after 2 again 3 will come and 4 will come. So this is how the array is. So we working with circular array is always tedious, right? So that's where one smart trick to deal with this circular array thing is just to replicate the array. So let's say the given array is 2 2 3 4 1 3, right? And you want all possible subarray of some length k, right? And the given array is circular. So what you will do, you will simply replicate the array and then and do the exact same thing what you would have done in the original array, right? So for example, let's say k is 4. So we want all possible subarray of length 4, right? So this is the first subarray, right? And then you will say this is the second subarray, this is the third one, right? Now for fourth one, you can simply like slide your current markers. This will be your fourth subarray, right? This will be your fifth subarray, and this will be your sixth subarray, right? Notice that how easy this had become. So in we so every time a circular array is given, just try to replicate the original array twice, and you will see you can get everything that you would want to get from a circular array, right? So let's just get rid of circular thing now, and let's say this is our given array 223413, k is 4, and we want to solve the exact same problem. The problem was we want to make each of these subarray of length 4 has should be having equal sum. That's what we want, right? Now let's think about it. We have these values. Let's just name it ABCD, right? So uh, sorry, let's say we have named it ABCDEF. So these were the six values 223413, and we have, as we have discussed, will replicate it just to deal with the circular stuff, right? And we just named this ABCDEF. Like all we have named this with different uh, characters. Now we want to make sum of subarray of length 4 equal. So currently this is the length 4 subarray, right? This has sum of a plus b plus c plus d. That's what the value of sum here is, right? Now let's talk about the second one. So what sum it has? It has b plus c plus d plus e. Now this b plus c plus d plus e should be equals to a plus b plus c plus d, right? That's what we want, right? So what does this indicate? This indicate that e should be equals to a, right? Otherwise this is not possible. Again, just to reiterate, what we have discussed was like the first subarray sum is equals to a plus b plus c plus d, right? The second subarray sum is equals to b plus c plus d plus c, right? And we want these two subarray sum to be equal. Only way this can be equal is this number should be equal to this number, because all these three numbers are common in both the subarrays. So only difference is the first and like this number and this number. So these two numbers must be common to make the sum equal, right? So that's where we are saying that e is equals to a. So we have written that e is equals to a. Now let's move forward. We want to make this sum c plus d plus e plus f equals to the other two, which is a plus b plus c plus d or b plus c plus d plus e, right? Now if you think again, what does it has? C plus D plus E plus F. Now E was equals to A, right? So what did it have? It have C, D, A and F. And what does original subarray have? Original subarray had A plus B plus C plus D. And current subarray has C plus D. This is A, right? Because we just have figured out that. So this is A and this is F. So what is missing? Missing is B. So F must be equals to B, right? Otherwise, it is not possible to make C plus D plus E plus F equals to A plus B plus C plus D, right? Hope you are getting it. So in the same fashion, if you continue, you will see that this to make this sum equal again, you have to make A equals to C, right? And further on, this B will again be equals to D. So just to reiterate this part once last time, let's say the sum is the sum current sum is E plus F plus A plus B, right? And we haven't figured out yet, right? This part. Now, what we know is E is A, F is B. This A is also equals to C, right? Now, what is missing here? Missing here is D, because the original sum was A plus B plus C plus D. So three things were there, and now only thing missing here is D. So that concludes that B must be equals to D. Otherwise, it is not possible, right? So that's how we figure out that B is equals to D. If you follow the exact same trick and continue this, you will see C is equals to A, D is equals to B, and E is equals to C, and F is equals to D, right? So basically, what we are doing is We are just repeating a plus b, like a b c d, uh, one more times, a b c d, then again a b c d, and then again a b c d, right? So that's what we are doing. Now, if you think about it, what does it mean? It means that a and e should be equal, c and a should be equal, right? Similarly, b and d should be equal, d and f and b should also be equal, right? So it means we are kind of forming groups, right? And whenever group structure comes, the first thing that should come to your mind is disjoint set union, or DSU, right? Again, why DSU? Because we know that E is equals to A and A is also equals to C. So we finally need to know which all elements are equal to each other, right? That's where we are taking the help of DSU, because that's what DSU is built for. We need to, like, if we want to make groupings, DSU will help us, right? So let's just take one concrete example and try to understand this part again. So yeah, so let's say this is your array, right? And k is 4. So we need to make every subarray of size 4 equal. So array was like array element is 223413 itself. I just marked the indexes here. So there are 6 indexes, 1 2 3 4 5 6, right? So these are the 6 different indexes. The values are still 223413. So values is something which is not changed. Now, as we have previously discussed, what we will be doing, we will just be, if k is 4, we will be repeating k again and again. So instead of ABCD, I just marked this as 1 2 3 4 this time. So 1 2 3 4, 1 2 3 4, and 1 2 3 4, right? Now, the last three elements is something we will not consider. Why? Because we just need to consider all the subarray of length 4. Now, if you think about it, all the subarray of length 4 would end before the last three elements. So this is the first subarray, right? This is the second subarray, right? This is the third one, the fourth one, fifth one, and finally sixth one. Now, if you slide again, this subarray 1 2 3 4 is exactly equals to the initial subarray 1 2 3 4, right? So this subarray is something we don't want to consider because it is something which we have already considered, right? So in a sense, if you have n elements, in a sense, if you have n elements in the array and you want to understand how many subarrays of length k are there, the number of subarray of length k would be n plus k minus 1, right? So this is, you can just simply, sorry, not n plus k minus 1. Basically, you need to understand how long to go. You have to go until n plus k minus 1, right? And how many subarrays are there? You can just simply slide it and you will get it. So in total, there will be n such subarray, right? Now, uh, we know that this will be your groupings. So 5 will be equals to 1, right? 6 will be equals to 2, 1 will be equals to 3, 2 will be equals to 4, and finally 3 will be equals to 1. So what we will simply do, we will simply call merge on each of these. So this merge is the standard DSU merge. I am not explaining what merge, like how exactly merge is implemented in DSU. We'll look at it while looking at the actual code. But for now, I assume that you know how to like how merge happens in DSU. In case you don't know, just take this as a black box. Basically, just assume that if you call DSU with 1 and 5, it will merge 1 and 5 and will give you one leader for 1 and 5, right? So basically what we're doing is we are merging 1 and 5, we are merging 2 and 6, right? We are merging 3 and 1, 4 and 2, and finally 1 and 3. So we are calling merge on each of these. Now after you call merge, what will happen? It will group, right? So if you see, this will be your groupings. So there will be one leader which like the leader can be anything between 1, 3, and 5. So I just assume it to be 1. So there will be one group which have three elements, 1, 3, and 5, and there will be one group which have two element which have three elements, 2, 4, and 6. So what does it mean? It means that first, third, and fifth index must be equal. Similarly, second, fourth, and sixth index must be equal. So what does it mean internally? It means that what was the first index? First index is 2, right? What was the third one? Third one is 3, and fifth one is 1. So we need to make every element in this array equal. And for this, we can simply reuse the function that we have discussed previously in the uh, earlier part of the video, right? So this is the first part, and then we have another group which says 2, 4, and 6. We need to make all this 2, 4, second index, fourth index, sixth index equal. Second index has 2, fourth index has 4, and sixth index has 3. So we need to make 2, 4, 3 equal. So now what is the answer? Answer is number of operations required to make all the elements in this array equal, plus number of operations required to make all the elements in 2, 4, 3 equal, right? This will be your final answer. Again, uh, just to make this concept a bit more clear, let's take one last example, and let's conclude this. So let's say this time k is equals to 5, right? And we have exact same array, right? So if you think about this, it would look this time something like this: 1, 2, 3, 4, 5, 6. These are the six elements in the original array. But because k is 5, the repeat would be until 5. So 1, 2, 3, 4, 5, and then again 1, 2, 3, 4, 5, and so on and so forth, right? So 1, 2, 3, 4, 5 again after this. Now, once again, we will ignore everything after n plus k minus 1, right? Why? Because if you again look at it, this is the first subarray of length 5. This will be second subarray. This is the third one, fourth one, fifth one, sixth one. And if you go beyond this, basically you are considering the exact same subarray which we have already considered. So that's where this subarray is not valid, and similarly this subarray will also be not valid. So basically that's where we have ignored the last two elements, or in other words, we are going only until n plus k minus 1, right? So these, we will consider all this index. Now again, after this, we know what to do. We just want to group 1 and 6. We want to group 1 and 2. We will group 2 and 3, 3 and 4, and 4 and 5. So if you look at it closely, so this grouping is something again DSU will do for us, but just for this example, we will call DSU with all these merge values. And if you look closely, 1 is equals to 2, 2 is equals to 3, 3 is equals to 4, 4 is equals to 5, and 1 is also equals to 6. So basically every element here should be equal. So what we will get after we call DSU, we will get that there will be only one group which contain all the elements. In other words, we want all this element to be equal to make the original problem true. So the original problem was we need to make subarray of length 5, every subarray of length 5 equal. To make that happen, we figured out that it is necessary to group, it is necessary to these for these elements to be equal, otherwise it is not possible, right? And that's where we figured out that okay, uh, at the end it's saying that all these indexes should have equal value. In other words, it means that we need to figure out how many operations are required to make this entire array equal, or equal to a particular number x, right? And this is something we know how to calculate. So hope this entire problem now makes sense. Just to reiterate the entire solution once last time, what we are doing, what where we have started, we have started initially with the fact that we want every subarray of length k equal. Now we notice that if we want a subarray of length k equal, the next subarray only differs by one element. And because it only differs by one element, this element must be equals to the first element that was ignored in this subarray. So that's how we figured out that E is equals to A. And similarly, F would be equals to B, and so on and so forth. Now, after we figured out that, we kind of know that okay, we have to group these elements, or in other words, we have to group the we have to say that fifth element is equals to the zeroth element, first element, sixth element is equals to the second element, and so on and so forth. So from that logic we build out these two arrays. Basically, the first one is just the index, and second one is the abcd part, where we know which element will be mapped to the original element. So here we have kept 1 2 3 4 5 6 because we want to make everything here as distinct, right? So after this, we figured out that okay, sixth index should be equal to first index should be equal to second index, and so on and so forth. So we just use DSU to group all of these, and DSU finally will give us some groups. So in this case, it gives us one group, but in the previous example, we have noticed that DSU was giving us multiple groups. So it gives us two groups. Now, what does it mean? It means that all the element in this group must be equal for the original condition to be satisfied. The original condition was we need to make subarray of length 4 equal. So all the elements, all this element at index 231 should be equal. All the element at index 243 should be equal. Now, what that in turn means, it means that we can simply call the previous algorithm which we discussed, that how many minimum number of operations are required to make everything here as equal. So let's say we got uh, x1 x, or r1 from r1 for this array, r2 for this array. The final answer would be r1 plus r2, right? So this is the exact part. Let's look at the pseudo code, and then we'll look at the time complexity and close this. So let's keep it here. So the pseudo code would look something like this, and this is exactly similar to what we have just discussed. So initially we prepared this equal array. Equal array is nothing but this particular array that we have built. So it just repeats k 2n number of times. So we prepared an array of size around 2n, and we repeat this 1 2k 1 2k 1 2k in this fashion, right? So the simplest way to do this is these two loops, right? Now after we build this entire equal array, we have to merge these indexes, right? So that's where we will use DSU, and we just call merge on these indexes. So what we are saying is we haven't built the first array explicitly here, so that's where we are deriving first array on the fly. So if I is, so let's say I is this, so if I is less than n, then we will merge I with the equal value. But if I is greater than n, let's say this, so then we will merge 3 with 4, right? So basically we will merge n minus I. So if you look at the index, it would be 9. So you will merge 9 minus 6 from the array. 9 minus 6 to 4. So that's what we are doing. If I is less than n, we will merge I, otherwise we will merge I minus n, and we'll be merging this particular index with the index at equals of I, right? So after this entire step, DSU will have formed groups, right? And finally, we will query the groups from DSU. So this is how we are querying the groups. So to query the group, what we are saying is we are just iterating over all the indexes and figuring out what is the leader for each of those indexes, right? So if you know about DSU has two concepts, uh, sizes and leaders. So basically every index, once it merges all the index, it will assign all the index of a particular group a same value, right? So it will assign, like if you query the leader of 2, you will get, let's say you are getting j, if you query the leader of 3 as well, you will get J. If you query leader of 4 as well, you will get J, and so on and so forth. So basically, what we are doing is we are just grouping out the elements or the indexes which have the same leader, right? But we don't need these indexes. Finally, we need these values because we need to make these elements equal. So this says that all these indexes should be equal, but finally we want that all these elements should be equal. So that's why instead of pushing I, we are pushing array of I, basically the exact value that we want, that would come in this particular group. Now after we formed group, the rest part is very simple. We just called make everything equal on all the groups. So this make everything equal is the exact same function that we have discussed previously. So this particular piece of code, right? Now, what is the time complexity? The time complexity is straightforward. So this entire thing would run in order n or order 2n for um, exactness. So this entire thing is order n, right? Notice that there are two loops, but we are not iterating over two loops completely. So basically, the first loop go over 0k 2k, and second loop goes over 0 to k. So in a sense, it would be order n. Now, second part, we are calling merge n times or n plus k minus 1 times. Now, merge in DSU with path compression is almost order n or order 1. So this entire thing would be order n, right? So calling merge is order 1. We are calling merge n plus k minus k number of times. So this will be order n plus k. So k is less than n, so that's why it is order n. And now finally, we are querying leader n number of times. So again, leader is also order 1 if we have done path compression. So this is again order n. And finally, we are calling make everything equal some number of times. Now notice that this make everything equal will be called, let's say, n number of times, but over this n, the size. So okay, first of all, what was the complexity of make everything equal? It was order n, right, where n is the size of the array. Now if you think about it, the total size of the array across all these I would be n. So the amortized complexity of this particular thing would be order n. So everything is order n, so entire solution would work in order n time, right? So I know this is bit involved, but if you have watched till this point and you don't understand any particular part of the video, I would include every possible timestamp in the description down below. You can move back and forth in the video and try to rewatch the section that you think that you don't understand. But I would strongly encourage you to pause here and try to code this entire thing yourself. If you don't know about DSU, just pick DSU function from my code and implement the rest of the piece yourself, right? Because that would actually help you understand this problem a much more in a much more better way, and you'll be able to apply this exact same trick in other future contests as well. So with that, let's jump into the code right away. Okay, there is one more thing before we move on there. So this DSU part, like this grouping that we have figured out with DSU, this 231 and 243, right? This grouping can be figured out easily with some observation as well. So if you have made some observations here, you will see that the grouping is nothing but the GCD of n and k, but that would require observation, and that is a bit harder to come. So that's why I haven't discussed that, but I will show the code for that as well at the end. So for now, this is what the code is. So first we calculate the equals array. Equals array will just populate everything from 0 to k, 0 to k, or 1 to k, whatever, like whichever index you prefer. Now once you prepare this equal array, we are just calling DSU merge. This is exactly similar to what we have seen in the pseudo code. So we want to merge these two indexes, right? Now this index is index 7 actually, but we are merging index 1 of the original array, right? Because this is circular array, right? So we are merging index 1 of the original array. So that's why this I minus n is there if I is greater than n. Now after we perform this merge, we just simply group them, right? We have discussed this thing in the pseudocode part, and after that we just call make everything equal on each of the groups, right? Now let's look at make everything equal and DSU part as well. So first let's go through make everything equal. Now this function is exactly similar to the other pseudocode that we have looked at the initial part of the video, basically this part. So what we are doing is if array is empty, we return 0 here because we don't want to deal with negative indexes at all. After that, as discussed, we'll first sort the array, right? And then we calculate the prefix sums because prefix sum is required to calculate the sum of the right half and the left half of the array, right? So that's why we calculate the prefix sum. Now, next thing is we are trying to make every element equals to array I, right? So what we are doing is we are calculating number of elements in the left. So if you remember, just to reiterate this part, so if you want to make everything equals to 2, we need to first understand how many elements are there in the left, what are their sum, and we'll simply subtract the current sum from the desired sum because we know every element here would be increased, right? And because of this particular statement that every element would be increased, we can simply subtract them and that would give us the right value, right? And similarly for everything in the right, because everything here needs to be decreased, we can simply sum them as well and subtract it with the desired sum. So this will give us how many decrements are required, right? So we calculate a smaller number of elements smaller than I, number of elements larger than I. We calculate the number of the sum of all the elements which are smaller than I, sum of all the elements which are smaller than often sorry array I, and finally we calculated what it requires to make all the right elements equals to array I and all the left elements equals to array I, and we just sum number of operations and take it with like take this with the current result that we have, right? Now, last thing, DSU. So this is standard DSU. I will not discuss in much depth, but just to give you a glimpse. Um, what we are doing here is we have two array, parent and size. We initialize both of them. Like size is initialized with 1. So basically it says that each group currently has its own element only. So basically every group is separate 1 2 3 4 5 6, and each group has one element only. That's what size denotes. Now what is parent? Parent is like we are like in DSU we will be forming a tree like structure, not exactly tree like structure, right? So that's where like parent denotes the immediate parent of a particular node. So initially every node is parent of itself. Basically there is no other parent apart from that particular node, right? Now let's look at the merge function first. So what merge function is, we are merging two things. So in DSU, as we have discussed, like each node would have each group would have some nodes. So let's say this is one group, this entire thing is one group. Now let's say we are asked to merge this group and there's one more group like this, right? And we are asked to merge this node with this node. Now in DSU, what we do usually is we'll not merge directly these two nodes. Instead, we merge their leaders. So these two are the leaders of this. This is the leader of this group. This is the leader of this group. So we say that okay, these two leaders will be merged. So that's why we have found the leaders of U and leader of V. If leaders are equal, it means they are already merged. So if let's say the function is called for this node and this node, then the leader of these two nodes are same. So this means that these two nodes are already merged. So we will just return from the function. Otherwise, this is just one operation to save a couple of lines. But what we are saying is we will make parent of u to v. So basically we will just attach this link. So we'll say that parent of this node is now this node. So this is the leader of this entire thing now, right? So that's what we are saying with this statement. And finally, because this is the leader of this entire thing now, the size of this group has now increased by this much amount. So size of this group has now increased with this much amount, right? And finally, the leader part. This is straightforward. If this node is the doesn't have any parent at all, it means this is the leader, right? Otherwise, if it has a parent, we have to find the leader of that particular parent, right? And that's how we'll get the final leader. Now this assignment is a part of path compression algorithm, which help reduce the time complexity of this entire thing. But discussing that would be very huge, so we'll keep that for another discussion. So hope you got the solution. If you have any doubts in any of the parts of the problem, feel free to post them in the comment section below, and I would be happy to answer. Just to show one last thing before we conclude. So this is the code that I was talking about, the GCD one. So we don't need to actually do DSU. If you have figured out some observation that we can simply figure, like the grouping can be done based on GCD. So if GCD is, let's say, X, we can just group uh, 0, 0 plus X, 0 plus 2X, 0 plus 3X, and so on and so forth. So that is just one observation that can avoid DSU. But I would strongly encourage you to understand the DSU part of the problem first, because observations are something that you might not be able to make in a real life contest or a real life interviews. So this basics is something that you should be very clear with. So with that, we'll conclude. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.